Hi, in this video I'm going to work through 3 examples of hypothesis testing with the normal distribution. Okay, so let's read the question and pick out all the key information. So we've got a company is selling fruit juice in cartons. The amount of juice in carton has a normal distribution and a standard deviation of 3 millilitres. The company claims that the mean amount of juice, mu, is 60 millilitres. A trade inspector has received complaints that the company is overstating the mean and he wishes to investigate this complaint. The trade inspector takes a random sample of 16 cartons and finds that the mean amount of juice per carton is 59.1 millilitres. Use a 5% level of significance, state your hypothesis clearly, test whether or not there is evidence to uphold this claim. Okay, so in the first sentence, we're told the standard deviation of the juice, and in the next sentence, we're told the mean. So we can say that X, I'll call it X representing the amount of juice per carton, is normally distributed with a mean of 60 and a standard deviation of 3. Okay, we have got a sample of 16, so N is 16, and then that 59.1, that is our sample mean. So that's the observed value of the test statistic. Okay, so the first thing we're going to do, and I'm going to show you both methods, so we would have to do this for either method. The first thing we would do is we would convert our parameters. So we've got the population parameter, so we need to change to the sample distribution. Oops. So X bar is normally distributed, so the mean stays as 60, and then the variance we need to divide by 16. Okay, so any calculation now, we're going to use mu is 60 and sigma is the square root of 3 squared over 16. Okay, and I tend to write that down because a really common mistake is to use the wrong standard deviation. Okay, so we've converted our parameters. The next thing we need to do is write our hypotheses. So the null hypothesis, we're assuming that the mean is as it's stated. And then the alternative hypothesis, well, the trade inspector says it's overstated, which means he thinks that it's less. Okay, so we've done everything we need to do. Right, so now we can do both methods. Okay, so I'm going to change colour. Let's go for purple. Okay, so the first method I'm going to do is the p-value method. Okay, and to do this, I'm going to use the normal CD function on my calculator. Okay, this method, if you've got the observed value, which we have, okay, is the easiest method. Okay, all we're going to do is we're going to say what is the probability of getting a mean of 59.1 or less. Okay, and I'm gone for less than because of that there. Okay, because it's the same. Get rid of that. Okay, so what is that probability? So if we use our normal CD, 59.1 would be the upper limit. So we could just put 0 in for our lower limit. We end up with a probability of 0.115. Okay, now what does that mean? So we're looking for a significance level of 5%, meaning in order to reject the null hypothesis, we need a probability that's gone below 5%. Okay, according to that, there is an 11.5% chance of getting 59.1. 11.5. So even though it's small, it's not that small, which means it's not particularly significant. Okay, we would need a teeny tiny percent chance of something happening, that if it was to happen, then that would be significant. So that 11.5% is not small enough to say that what the trade inspectors found is significant. Okay, so I'm going to say 0.115 is greater than our significance level. Okay, so we are going to fail to reject H0. Okay, and we're going to say there is not enough evidence to support the claim. Okay, so that 59.1 is not small enough according to the significance level of supporting that claim. So that's the p-value, and that 0.115 is the p-value. So if it says in an exam, state your p-value, then that's the probability. So it's the probability associated with the observed value of the test statistic. Okay, I'm going to rub that out, and then I'm going to do the second method. So the second method is the critical region method. Okay, so method 2 is the critical region method. So in other words, we're now asking ourselves, well, how small a mean would we have to get in order to reject? Okay, so this is using the inverse normal function. So if I draw a little normal distribution curve, there's my mean. My mean is 60. And we're saying, this is x bar here, we're saying what value, I'll just call it x, would have to be there such that that is 5%. So what would the mean have to be such that there's a 5% chance of getting that or less? So if we use our inverse normal now, because we have an area, so that 0.05 is the area, we end up with x, which is our critical value. So the critical value, x equals 58.77 millilitres. Okay, so the critical region, x bar, so the mean, would have to be less than 58.77. Okay, and since 59.1 is not in the critical region, then we have the same conclusion as before. Okay, so 59.1 is not in the critical region, it's not small enough, it is not significant, therefore we fail to reject the null hypothesis and we cannot support the trade inspector's claim. So either way, we are failing to reject. Okay, now in this particular question, it doesn't direct us on either method, so you could choose whichever you prefer to do, and as long as your conclusion, as long as you make some sort of comparison and then you conclude, then it won't matter how you do it. Sometimes they will require the p-value, in which case you will obviously use the p-value method. Sometimes it specifically says to find the critical region, in which case you've got to use that method. So you need to be able to do both, but in the event of having an option, then you can choose which one you prefer. Okay, let's have a look at another question. In 1985, the mean height of sixth form students was normally distributed with a mean of 168 and a standard deviation of 8. So that's in 1985. In 2015, it is claimed that students are now taller. A random sample of 50 students was taken and the mean was found to be 170. Test at the 5% level of significance that students are now taller. Okay. So, in 1985, the mean height, X, was normally distributed with a mean of 168 and a standard deviation of 8. Okay, in 2000, so that's what we know is factually correct. Okay, we've now got a sample of 50, in 2015. We've got where we've taken from our sample a mean of 170. So that's our observed value. That's our observed value. Okay, and we're doing a 5% level of significance. Okay, so because we've got the observed value and it doesn't tell us a particular method, I'm just going to do method 1. So the first thing I need to do is convert my parameters. So the mean stays as 168, the variance will be divided by 50, which means I'm working with a standard deviation of the square root of 8 squared over 50. Okay, and I'm not simplifying that. You can do if you want, but I just tend to leave it like that and the calculator will sort it out. Okay, as long as I know to use the right one. Okay, so I'm going to use the p-value method. I'm going to use normal CD. Okay, we want our hypotheses. Okay, so in the null hypothesis, mu is 168. The alternative, well, we're looking to see if students are now taller, so we now are looking to see if mu is now more than 168. Okay, so we're after the probability that x bar is greater than 170. So we're using normal CD. There's 168. This is my x bar distribution. There's 170. And we want to know what that probability is. Okay. Is it significant? What are the chances of having a mean of 170 or more? Well, the probability is 0.0385. So that's our p-value. That's the p-value. Okay. What does that mean? Well, there's only a 3.85% chance of getting 170 or more, which is smaller than 5%. So there's only a 3.85% chance. That's smaller than the significance level. So there's a tiny percent chance of it happening, but yet it's happened, then that must be significant. Okay, so I'm going to say 0.0385 is less than our significance level. Okay, so we are going to reject H0 and we're going to say that there is enough evidence to suggest students are taller in 2015. Okay, so that's that example. I'll just do one more. Okay, a machine produces bolts of diameter D, which has normally distributed with a mean of 0.58 and a standard deviation of 0.15. The machine is serviced, and after the service, a random sample of 50 bolts from the next production run is taken to see if the mean diameter of the bolts has changed from 0.58. The distribution of the diameters of bolts after the service is still normal with a standard deviation of 0.15, so that's not changed. Find at the 1% level the critical region for this test. Okay, so D, it says, D is normally distributed with a mean of 0.58 and a standard deviation of 0.015. We've got a sample as our sample, so N is 50. Okay, and we're asked to work out the critical region. So we've got no observed value yet, so we're asked to work out the critical region. So I'm going to change my parameters. D is normally distributed with a mean of 0.58, that's unchanged. The variance is divided by the sample, which means that sigma that we're working with is the square root of 0.015 squared over 50. So that's what we're working with our standard deviation. So I've changed my parameters. Now we need some hypotheses. So H0, mu is 0.58. Now this time it just says see if the mean diameter of the bolts has changed. So it doesn't say in which direction, which means we've got not equal to, which means we are doing a two-tailed test. Now all that's going to be different here is if we're doing a two-tailed test, then we need to halve the significance level. So instead of using 1%, we're going to be using 0.5%. Okay, we're looking for a critical region. So in terms of our diagram, we'll just do a little picture. Rubbish curve. We'll do 0.58. Okay, so this is D bar distribution. Okay, saying there is going to be some value here. I'll call that D1. And some value here. I'll call that D2, such that that is 0.5%, so 0.005, and that is 0.5%, 0.005. Okay, so we're using inverse normal because we have an area. So if I work out D1 first, and we want the area to the left, so 0.005, if you put that in your calculator, so 0.005 is the area, that weird horrible thing there, square root of 0.015 squared over 50 is the standard deviation, and 0.58 is the mean. Okay, that'll tell you what D1 is. So at the left-hand tail, that'll tell you that that is 0.5745. Okay, now for D2, you've got two options. You can either substitute area is 0.995, remember you need the area to the left, so it's going to be 0.995, or alternatively, you could just use the symmetry, because remember this is symmetrical about the mean, so you could just work out how far D1 is away from the mean and then add it on. Okay, but either way, you should get 0.5855. Okay, so that gives us two critical regions critical regions, D bar is going to be less than 0.5745, or D bar is going to be greater than 0.5855. So those are our critical regions. Okay, and then for part B it says the mean diameter of the 50 bolts is that. So that's our observed mean. So that's what we've got. So now we just need to comment on this in the light of the critical region. So we just need to decide, is that significant? Is it in the region or is it not? Okay, and in answer to the question, it's in the region, isn't it? It's in that region there. So I'm going to say 0.587 is in the critical region. Okay, which means it's significant, which means we can reject H0. Okay, and we can say there's enough evidence to suggest the mean diameter has changed. Can I squeeze it on? Okay, I'm not saying in which direction it's changed. I'm not saying it's greater just because it happens to have fallen in the top tail. I'm just paraphrasing what it's asking me in the question. All we know that it's changed. Okay, that's all we've concluded. There's enough evidence to say that it's changed. Okay, so that's the end of the video. Keep practicing. Do lots and lots and lots of practice on this so that you've got it all clear in your head.